electric dipole. Second case, the electric field at an equatorial point. Electric field at an equatorial point. Equatorial point of an electric dipole. So we need to find electric field of an electric dipole. Now in this case it is at an equatorial point. What is equatorial point? For that, so let me take a dipole. Suppose, what is a dipole? So a dipole is a setup of two charges. One charge is negative charge, another charge is positive charge. So these two charges are separated by a distance, so that we are known as dipole length. The dipole length we are mentioning as 2a. 2a is the dipole length. And from negative charge to positive charge, what is there? Dipole moment. So P bar is the dipole moment direction. So dipole moment direction is from negative charge to positive charge. And so here itself I can explain one more time what is dipole moment. Dipole moment P equal to the product of magnitude of either charge. You can take just the magnitude of the charge times dipole length. So here the dipole length equal to 2a. So P equal to 2qa is known as dipole moment. And the dipole moment having direction, the dipole moment P bar equal to 2qa times P cap. Here P cap direction, P cap is a unit vector for the dipole. So its unit vector direction is from negative charge to minus charge to positive charge. So this is the concept of electric dipole and dipole moment direction also. Now we need to define same electric field for an electric dipole, but in this case at an equatorial point. So for the equatorial point, let me consider again a dipole. So let me take a negative charge and here a positive charge. Now the distance between them equal to 2a. So that is the distance between them is 2a. And the dipole moment direction P bar is minus to plus charge. Suppose if I select perpendicular to this axial point, perpendicular to dipole axis, it means if I select a point at here or at the below the down at here, it is exactly perpendicular to the dipole axis. If you select a point perpendicular to the dipole axis, so this point we known as equatorial point. So now our task is to find the electric field due to this electric dipole at here. So that is the case, electric field at an equatorial point of an electric dipole. To find the electric field due to electric dipole at an equatorial point, let us draw a figure. So this is the electric dipole of the dipole length 2a. Now let me consider a point P at here So I need to find what is the electric field at there. So this point P is along the equatorial line. So the equatorial line is the perpendicular from the dipole axis. So at point P, electric field due to because of the negative charge also exists, and due to because of the positive charges also exist. To find the electric field at point P, so according to convention, what shall we do? We will bring a positive test charge. If I bring a positive test charge at point P, and here the source charge also plus Q, so these two will be repel each other. So let is the electric field directions at that point. So the electric field directions at that point is somewhat like that. So this is the electric field due to plus Q charge in that direction. And what is the electric field due to negative charge at point P? Since it's a negative charge, the negative charge will be attract positive test charge. So now this is the electric field direction due to because of the negative charge, due to because of this charge. Now I need to find the resultant electric field at point P because of these two electric fields. To find the resultant electric fields, what we have to do? So we need to bring a coordinate system at there. So let me take a coordinate system. So if this is the coordinate system at point P, I would like to highlight that with this blue color. Yeah. Now clearly you can observe that. So this electric field is in this coordinate. If you can take that negative x-axis and the positive y-axis. So now we have to resolve this electric field into components. And similarly, this electric field due to the negative charge is also will be resolved into the two components because it is in the negative x-axis and the positive y-axis. Okay. Now to do that task, so we need to find out what are the corresponding the angles. Suppose if this electric field is making an angle theta with the x-axis, it means this electric field, if you can take an angle theta along the x-axis, here it is angle theta. Now this electric field will resolve into two components. So that two components are horizontal component and vertical component. So that components I can mention it here. So this is the horizontal component, it is the vertical component, and at the same time, so here it will be the one more the horizontal component. So the horizontal component and vertical component electric field due to positive charge. And similarly, we are having electric field due to the negative charge. So if the negative charge is making an angle, if the negative charge making an angle with the x-axis theta, again this electric field to the negative charge will also resolve into two components. So that two components are horizontal component and vertical component. So again on the same x-axis we will get one more component due to because of the negative charge. So that will be along in the same direction, and we will get one more electric field component exactly opposite to the positive y-axis. So that will be the along in this direction. Now what is the resultant electric field? So the resultant electric field at here, since these two components, positive and the negative, they both are equal and opposite, they cancel each other. The vertical components, that is electric field due to positive charge along plus y, and electric field due to the negative charge along negative y, they are equal and opposite, so they cancel. So if they cancel, our burden will become less. Now we need to find out what is the electric field due to the rest of the two components. The rest of the two components are as, since it is theta, so the electric field due to the term we can take as cos theta. So that I can take as electric field due to positive charge eq cos theta, and another term we can take as electric field due to E minus q cos theta. Now what is the total electric field? The total electric field, we need to add these two terms. So if you draw any neat clean diagram at here, so the horizontal components, they both will be gets cancel each other. Sorry, the vertical components, they gets cancel each other, and only the horizontal components, they will add up each other. So finally I can write that electric field at an equatorial point is sum of the two components. For that, first we need to write what is the electric field due to positive charge and what is the electric field due to negative charge. Now electric field at point P due to plus q charge. What is the electric field formula? Electric field E due to plus q charge equal to 1 over 4 pi epsilon naught times charge q upon the distance from the point where we are calculating electric field and where is the source charge. If R is the equatorial point where we have chosen, and A is the half of the dipole length at here, by using this right triangle, so we can calculate the what is the distance from the point P to charge Q. So if we can apply the Pythagoras theorem right at there, so we can get that value. Here it is r square plus a square whole square. So under root of r square plus a square, and if you can do the a square there and root gets cancels, so the electric field at plus q charge equal to 1 over 4 pi epsilon naught q upon r square plus a square. And where is the direction? So if you want to mention the direction is, so you can mention the direction. Now I would like to mention the direction along B to P. Yeah, this line is showing along the B to P, so it is along the B to P. So that is the electric field due to positive charge. And what is the electric field due to the negative charge? So I would like to write the what is the electric field due to negative charge. Electric field due to minus q charge at point P. At point P, so that you can write as, so electric field due to minus q charge electric field due to minus q charge equal to 1 over 4 pi epsilon naught times the magnitude of the charge here equal to plus q by the distance. So in this case the distance also the same the length. So what is the distance at here? So r square plus a square. This side also becomes r square plus a square under root. So that value we can substitute at here. So q upon under root r square plus a square and whole square. So square root gets cancelled. Electric field due to minus q charge equal to 1 over 4 pi epsilon naught times q by r square plus a square. And now direction, its direction is along. Now it is due to because of the negative charge, it is acting along a to p. Okay, now if you observe these two electric fields, electric field due to negative charge and electric field due to positive charge, their magnitudes are equal. So magnitudes are equal but directions are the different. That's why the resultant electric field is changes. Now to write the resultant electric field, since the electric field is having components, so the components normal to the cancels out. Now the components of minus charge, electric field due to minus charge and electric field due to plus charge normal to the dipole, axis will cancel. So again see it here. So these two electric field due to positive charge component and this component, and electric field due to these components, so they both are equal and opposite. So they both are equal and opposite. What happens? Those components will becomes vertical components, they will becomes cancels each other. Now if they cancel each other, which are the components are left? So the leftover components, the normal components, the components parallel to the dipole axis will add up. If they add up, we need to write the electric field, total electric field at equatorial. So I can mention as EQAL, electric field due to equatorial, equal to these two components are the cos components. So which are the components that? So these two components, electric field due to EQ cos theta and E minus Q cos theta. So we need to add that two components. So that is E plus Q cos theta plus E minus Q cos theta. So this gives the magnitude of the electric field. But what about the direction? The direction of the electric field at here you can see the direction of the electric field at here, it is in the negative x-axis. So but we need to represent that by comparing the dipole moment. If you take dipole moment along the positive x-axis, and the resultant electric field at equatorial point is opposite to the dipole moment. So the direction of the electric field at the equatorial point to mention, so I can mention it here minus sign along with the p cap. So here negative and p cap tells about the direction of the electric field. So now at equatorial point, the electric field direction is opposite to the dipole moment direction. So that's all about the electric field final expressions. Now it's easy. We need to substitute what is the electric field to the positive and what is the electric field to the negative and cos terms. So electric field due to equatorial equal to negative of what is the plus q value? It is a 1 over 4 pi epsilon naught q by r square plus a square times cos. From the triangle you can write the what is the cos term. So from this triangle AOP, from the triangle AOP you can figure it out what is cos theta. Cos theta equal to A upon base by hypotenuse, A upon square root of, here hypotenuse equal to A square plus R square. So we can substitute that. A upon square root of A square plus R square, and the electric field due to the negative charge is also same term, 1 over 4 pi epsilon naught times q by R square time plus A square of, there also cos term goes to A upon square root of R square plus A square, and the direction is along the dipole moment. So now you can add the two terms since they both are equal terms. Negative of 2 times 1 over 4 pi epsilon naught q by r square plus a square times a upon square root of a square plus r square. The direction, the negative sign, and the dipole moment direction. Now for the simplification, the electric field due to equatorial point equal to negative of, if you see these terms 2qa, these all on the numerator, so that I can write as dipole moment. Dipole moment formula, the product of charge and dipole length. So this I can call as dipole moment. So that equal to P upon, on the denominator 4 pi epsilon naught, and here these two terms are same. You can combine these two terms and you can write r square plus a square whole power 3 by 2, and final direction P cap. Now, so this is the final expression, the electric field at an equatorial point because of an electric dipole. So this expression having both magnitude and direction. So the direction of the electric field is opposite to the direction of the dipole moment in the equatorial condition. But in the axial condition, they both are in the same direction. Now let us apply a case. The case is as usual. If you take R, the point, equatorial point is very much greater than the distance A, and we will neglect A in denominator. Therefore, electric field due to equatorial point, it's a negative of P upon 4 pi epsilon naught R square whole power 3 by 2. If you can cut these terms and you can simplify that, so the final expression, the electric field due to equatorial point, so electric field due to dipole at an equatorial point equal to negative of P upon 4 pi epsilon naught R cubed. To compare the electric field equatorial point and axial point, if you can see, this is the electric field due to equatorial point. And if I show the electric field due to axial point, so which I calculated in the earlier case, so this is the electric field due to axial point. So the electric field due to axial point having a factor of 2. So if I take these together, so this is the electric field due to axial point and this is the electric field due to equatorial point. So here I mentioned P cap. So here you can combine axial point and equatorial point. So they both are in terms of the magnitude not same. It means electric field along axial point is greater than electric field due to equatorial point. So how much greater? In terms of magnitude, if you can write electric field due to axial equal to 2 times electric field due to equatorial. And not only that, if you can see the directions, so in the axial case, the directions here it is positive. It means electric field direction and dipole moment direction are same in axial condition. But in the above case, if you can see in the equatorial condition, electric field having negative sign. So the negative sign shows about electric field direction and dipole moment directions are opposite in equatorial condition. So finally, these two are the comparisons between electric field due to an electric dipole. So for an electric dipole, the electric field is strong along the axial line, and along the axial line the electric field direction and the dipole moment direction, they both are in the same direction. But if we take equatorial line is a point along the perpendicular to the dipole axis. So at that point electric field is less than the electric field due to axial point. And at an equatorial point, the direction of the electric field and the direction of the dipole, they both are opposite.